All right. Hello, everyone. I hope that the audience has already saturated so we can start. So I would like to welcome you back to our colloquium series. So this semester, there will be a lot of exciting talks, and we'll be hosting experts from many distinct fields that are relevant to electrochemistry. So I hope that you will be enjoying the talks. And today, we're going to discuss a topic that is very important to the development of batteries, and that is the electrochemical stability of electrolytes. So as you know, any liquid system can accept or donate an electron to the electrode, as long as the potential drop at the solid-liquid interface is sufficiently high. However, even the simplest reactions today that involve electrolyte decomposition, such as water oxidation or, say, CO2 reduction, are in fact really poorly understood. As of now, we're still heavily struggling, I would say, with quantitative prediction of the rates of such reactions. And so now the chemistry of battery electrolytes can be far more complex. And getting even a glimpse into these heterogeneous decomposition processes for such electrolytes would be certainly amazing. And so this is why in today's colloquium, we're hosting Oleg Borodin from the US Army National Lab, who is a well-recognized expert in molecular modeling of complex electrolytes, polymers, and other media, and who will be discussing with us today the fundamental principles of the quantum chemical calculations of such electrolytic systems, and hopefully the current state of the art in this field. So maybe I should mention that Oleg received his PhD at the University of Utah in the year of 2000 and stayed there until 2011 as a research assistant professor. And then since 2011, he's being a scientist at the Army National Lab. So with that, Oleg, please, now the stage is yours.
Thank you, Andre. So today I'm going to talk about how molecular modeling can assist in battery design by providing fundamental understanding and some clues for what reactions are happening, so we can actually choose with knowledge how to tailor electrolytes for lithium batteries. And before I begin with the scientific talk, I want to acknowledge contributions from Travis Pollard, who performed the majority of DFT electrode solvent calculations, and Bon Oppenheimer and Janelle Watanabe, who worked on a double layer calculations, which I'm going to be showing. And I couldn't have done it without support from Chanson Wang, Kanju Group, Gleb Yushin Group, and Shirley Mann Group. They really provide so many ideas for back and forth, and so it's great. So look forward to your questions. Okay, I'm trying to. Okay, good. So what I'm gonna talk today is molecular modeling, specifically density functional theory modeling and molecular dynamic simulations. But we want to apply it in order to get understanding of electrolytes for lithium batteries. And the typical lithium battery is shown here. It has the cathode, anode, and electrolyte. And during charging process, we are putting electric field polarizing, so lithiums are moving from a cathode, they desolvate, go to electrolytes, through electrolyte go all the way to the SEI. And on the discharge process, the opposite happens. And in lithium-ion batteries, we want to have the most of the energy density possible, so we're always pushing an envelope how to enable more aggressive chemistries on both anode and the cathode side. And often electrolyte is a limiting factor because majority of electrolytes, as I will show, they are not thermodynamically stable on both anode and the cathode. And when they are not stable, they do decompose and form a solid electrolyte interface, which is ionically conducting but electronically insulating. It also has to withstand all the mechanical deformation associated with the growth of both anode and the cathode. So in molecular modeling, what I'm going to talk is understanding oxidation reactions, my favorite topic, and goes through historically how I kept thinking about it and my views evolved on what are relevant reactions? And one of the questions is not only what's happening, but how can we do the cheapest calculations and still get relevant answers? And these calculations will be done on both active and non-active electrodes. And the way how I'm separating them is active electrodes, those which wouldn't be, which will take a proton, so they participate in a reaction with an electrolyte during oxidation, and non-active electrodes, those which just take an electron during oxidation step, and all the reactivity happens. For example, glassy carbon is the most chemically inert, so that would be a non-active electrode, and oxides, phosphates, they would be active electrodes. Then I'm gonna take another view and try to correlate structure, because there has been so much effort on trying to understand the structure, and the questions comes, does it really matter what's the structure of electrolyte? And turns out that bulk structure, lithium coordination does matter for the reduction, and the double layer structure is the most important one for understanding of course not only reduction but for oxidation reactions. What also worked and is very important is trying to understand what is this solid electrolyte interface and how ions are transported, what's the extra ions and what's the local dipole, if you wish, right? Well, what the potential difference across the two systems like solid electrolyte interface and liquid electrolyte. So those are other questions which I will not be covering here. What I will be covering is primarily start with just the introduction of the battery, and is HOMA-LUMA adequate, when it is adequate, and what do we need to include in order to go beyond HOMA-LUMA. And I'm gonna drive you, hopefully you will agree with the conclusion that kinetics is really important at different potentials, because at different potentials, different reactions start taking place. And it's not just one oxidation process, it's a variety of oxidation processes which occur at different potentials. After that, I'll switch gears and talk about reduction stability of solvents and electrolyte and its the implications for SEI formation and composition. Follow with a double layer, and finally at the end I'll make a couple comments about lithium sulfur batteries and what we can glean from structural information which is relevant, I think, to understanding profiles of the charge discharge and mitigation of polysulfide solutions. So between each of this large segments, there are going to be 5-minute discussion, and the rest we'll have at the end. So let's move with a classical picture of lithium batteries, which I took a classic John Goodenough article, which is quite highly cited. So it's provides very nice intuitive understanding in the sense of given the electron energy. Here we have electron at rest in vacuum, or another, well, in this case it's electron at rest in vacuum as a benchmark. So the work function for the cathode is Fc. It's much larger than work function for the anode, and work function in this case just represents the energy you need to take an electron from the Fermi level and remove it from the metal and put it next to it, right? So it takes much larger energy to remove an electron from the cathode than the anode, and that gives rise to the electric voltage between two systems, which is OCV, roughly voltage. In order to choose an electrolyte, we can go two ways, right? We can choose a very low voltage between the cathode and anode, then electrolyte would be stable. But so, for example, if anode is has a work function which puts it lower than the chemical stability, electrochemical reduction of electrodes and electrolyte, then electrolyte doesn't reduce and it's stable. Once we put anode higher, electrons from here want to jump to lower energies, right? So electrolyte reduction will be happening. So we need to understand what is electrolyte reduction, and here consequently oxidation potential, and can it be correlated with homoluma of even each electrolyte component independently. What we are going to do, we are going to calculate the redox potentials, and in order to do that, we will use thermodynamic cycles. Essentially, in a thermodynamic cycle, we take a solvent, for example, like ethylene carbonate. In this case, we remove an electron, solvent deforms, which will be important, right? So the solvent is an electrolyte, so its side of EC is solvated. What we need to do, we need to move it and make it oxidized. At the same time, electron is going to be transferred to the electrode. However, that will give us the absolute electrode potential in vacuum. So on an absolute electron potential scale, essentially, instead of doing exact calculation, which is very hard, if we have explicit solvent, meaning that we take molecular dynamic simulations in which we put a couple thousand atoms inside of the box and solve Newton's equation of motion and sample the phase space, all possible configuration. It's hard to calculate. You need some reactivity, right? So it would have to be represented using a DFT at least, or some sort of, in order to handle the oxidation problem coupled with the salvation problem. So typically it's done much simpler ways that we can calculate salvation energy for the neutral molecule, salvation energy for the cation, and ionization potential, free energy, what it takes to oxidize the molecule in a gas phase. Right? Instead of doing explicit calculations, which are much more challenging, we are going to use implicit solvent calculation, in which solvent is surrounded by the polarized continuum with some dielectric constant, which makes a difference actually on both reduction and oxidation potentials. And typically the drawback that this model needs to be parameterized, and it's very sensitive to the radii of atoms which is used. Right. So on one hand, this model is the most accurate for organic solvents, but if you have lithium surrounded with something, then we will be including for salvation shell in order to explicitly consider it and use implicit solvent model for the rest of this. Right. So we can get absolute potential. However, what we're interested is getting not the absolute oxidation potential, but potential versus lithium. So we're going to do the same as lithium goes from lithium metal, sublimates in a gas phase, and then becomes a lithium ion. And it's the best to just use experimental value to complete the cycle. So when we couple two of these thermodynamic cycles, we come to very simple expression that it just we have a correction factor of about 1.37 or 1.4 from the absolute oxidation potential. And there is an important caveat which I think is often overlooked, that the absolute potential is different in different solvents, right? So that tells you that this correction factor is probably accurate within a 0.2 EV, 0.1, 0.2 EV, and you shouldn't look in much more if you're looking at the various solvent variations, right? So how do we do that in practice? It's very simple for those who haven't done it. Just take EC, take quantum chemistry software, Gaussian or games, perform geometry optimization inside of the implicit solvent, PCM, polarized continuum model, or simple salvation model by Trulla, and extract energy, right? So then the other thing which we need to remove an electron, create an oxidized species. We can do it using this geometry. That will be G at M. geometry, at the neutral geometry, and the difference between that will be called vertical oxidation. However, we can perform a geometry optimization. When we perform geometry optimization, geometry deforms significantly. There is a deformation energy, and that will be free energy at the cation geometry. So we can calculate two oxidation potentials. One I'm going to call vertical, when it's the geometry free energy calculated at the neutral molecule for the with removed electron minus energy of the neutral molecule divided by Faraday constant minus 1.4, and the adiabatic one when we calculate perform geometry optimization for both species. So in the sense of Markov electron transfer theory, we have acceptor and donor states. In this case, minima of both states that will be this E adiabatic, and if we do not relax geometries, then it will be a vertical oxidation, which is related to lambda and can be used to understand kinetics. So that's going to be my connection with the kinetics. So now let's go to what are relevant components. And when I started working in this area quite a while ago, I saw that majority of groups were just taking a solvent like EC solvent or PC solvent and calculating its oxidation potential, and often looking at trends. Because if you get the include polarized continuum and do geometry optimization and ensure by comparison with the NIST database that your ionization potential is actually quite accurate, you are still getting about 7 volts. Of course, if we had electrolyte been stable at 7 volts, we would be done. So clearly there is a disconnect, and EC is not getting oxidized by itself. So you have to be careful when you look at papers which say that, oh, we oxidized EC, decomposed EC, for example, and looked at the decomposition reactions. They might be relevant if you overcharge up to 7 volts, but I don't think that those reactions are relevant reaction pathways to your battery operation. So the breakthrough came when I put an anion next to EC, and I saw that once I remove an electron, then spontaneously a chair forms, so there is a deprotonation, defluorination, and if I calculate the that's the adiabatic oxidation potential, and so that's a vertical one, but we are looking at adiabatic, it's almost 1 volt below. So this deprotonation reaction in the presence of PF6, if PF6 accepts it, really stimulates decomposition of EC. Then started looking more, and it's not necessarily, don't need to remove fluorine from PF6. Carbonyl group of another EC can serve as a H acceptor. So if I take EC and another EC, remove an electron, reoptimize geometry, proton gets here to this group, potential becomes even lower. This reaction is even more favorable. If proton is shared between two EC molecules, it becomes even more favorable. If proton is shared and there is an extra anion to stabilize the whole, right, created by oxidation reaction, then the oxidation potential goes all the way to 5 volts. So there is a 2 volt difference. And then if I think, oh, would that be possible that after removing this hydrogen, right, the EC decomposes by opening up this bond and creating CO2 and a radical? What's going to be this energy? This process is very, very downhill. If it overcomes this 0.8, or depending on actually a cluster of 0.6 to 0.8 EV barrier, then the oxidation potential calculated relative to CO2 and the radical becomes 4.3 volts. So now that's within the voltage range of majority of battery electrolytes. And what we have lots of different reactions. Which one would be happening? And in order to try to make sense out of it, I thought that we can just loosely try to say that let's think in terms of Marcus electron transfer theory and this vertical versus adiabatic part, which accounts for the deformation and removal of hydrogen, H transfer, or the AC opening, right? I mean, in principle, it's clearly an extension. We are not going to have two nice parabolas like Marcus assumed in order to have lambda. But if we think in these terms, then we can unite all this picture and say that, well, that's going to represent kinetics of reaction. Kinetics is going to be the slowest here. And as we go to higher and higher potentials, then some other reactions will be activated, right? And they will have a much lower reorganization energy, that will be lambda, therefore much higher kinetics. So if we come with this point of view, then we can compare versus CV performed on a glassy carbon, which has done it in our branch. So if you took a 1.2 LiPF6 in an EC solvent and measured CV, that's in microamperes current, pretty small. And what you can see is that indeed current starts picking up at about 4.3 volts, keeps going up, and there is a very well developed oxidation for EC at about 6.5 volts. So roughly, that's a pretty good picture. Now, the next question is, can we account for what happens to EC versus EMC? And in principle, yes, we've repeated that, and much lowered electric constant makes stabilizes these complexes, so and makes it more favorable, leading to lower reduction potential in the case of EMC for the initial proton transfer. Next question is, do we always have a proton transfer? Because once you have proton transfer and decomposition, clearly anything related to the HOMO of the original solvent is just a trend. None of that is included in a HOMO-LUMA type of screening, which has been done and published. So that's a limitation of the previous work. And what I want to show here is that not all molecules have a H transfer. If we take VC and put VC between PF6 to stabilize it, and that's actually quite probable situation, as I'll show in a double layer, because anions really populate the cathode side, and I calculate VC oxidation potential. It's essentially close to 5 volts, but there is a huge gap in terms of reorganization energy. VC doesn't need much reorganization in order to get oxidized. Therefore, when we compare in milliampere hours now, the same electrolyte, but with 2% of VC, we observe a new peak at 5 volts, which gets about more than 2 orders of magnitude higher current than current for the EC decomposition due to this reaction. Actually here close to 5 volts. So that gets me a more or less unified picture, which says that we need to talk about kinetics and reorganization energy and include it in a screening of electrolytes, even on non-active electrodes, right? And non-active is actually important because if you think from the perspective of carbon additives, they're very small weight-wise, but surface area-wise, they're pretty large. So there is a lot of surface. And if oxidation occurs on those conductive additive surfaces, right, which it might not stick well to them, then we keep on oxidizing and decomposing electrolyte, and it's even much worse than passivation of the active electrodes. Right? So with this in mind, I just want to say that this same trend for VC being a much higher current, consistent with much lower reorganization energy, was observed here in ACV for glassy carbon, but also in Mark and Winter group when they used stable nickel manganese oxide spinel and looked at the stability, oxidative stability of electrolytes after intercalation. They observe that regular electrolytes have a similar behavior as what I showed. So those are LP30 to LP57. Those are ECDMC LiPF6 electrolytes, but this 572 electrolyte, that's ECEMC 3 to 7 with 2% of BC, very similar to what we looked here. And it does have an onset of oxidation potential with a very well-developed peak at about 5 volts. Right? So we do predict 5 volts, we don't predict 4.7, but that's a distribution which you can have distributed. So there could be an additional activation rates, which would allow the process to start a little bit earlier. So that seems like a nice unified picture, and that's what we try to apply for screening and understanding of behavior of different electrolytes at oxidation, non-active electrodes. So for example, in this case, we took solvents like EC with various anions. And let's start with the EC with TDY. I'm plotting here calculated results. Lambda is an approximation using a vertical minus adiabatic difference, right? So that's all the deformations occurring during oxidation step. And O and P are these points. In N point, we just take EC and TDY, which is cyano-containing anion, which Michel Armand has been working a lot. That has a pretty high oxidation potential. However, if nitrogen of the anion takes a proton, or if it takes a proton and reorients, that's point P, the stability becomes lower because EC decomposes. But it doesn't need very large reorganization energy for that. So similarly, next step, we looked at the half bulb, which is lithium D4B, these points K, L, and M. K point is here, the largest potential. Oxidation potential when it just oscillator group starts expanding, the D4B oxidizes by itself. If it oxidizes and then removes a proton and reorganizes, then points are lower. So and so on, we go through screening of all electrolytes. We do observe a very nice correlation between this predicted picture from DFT calculations, where TDY starts about 4.7 in reasonable agreement with experiment performed on glassy carbon, I think at 10 millivolts per second. Then D4B is the next one. TFSI is the next, and so that's TFSI, and EC BF4 is the last one in a good agreement. There are a couple caveats here that I used MO5-2X 631 cheaper DFT calculations, and in more accurate calculations, when we go to couple clusters, this energy tends to shift about 0.2 EV to lower voltages, right? So that needs to be kept in mind. But overall, trend-wise and picture-wise, I think it's a good picture for screening. Unfortunately, it's not a homolomorph solvent, right? Which is very easy to calculate. It's more complicated, but that's what it takes to start understanding battery electrolytes. So as the next step, we can think if carbonyl group can accept proton, if H transfer occurs to the nitrogen, why not oxygens or all cathodes, right? And after all, phosphate cathodes and oxide cathodes are the most used cathodes. So when we took the lithiated, most charged cobalt phosphate, it's a very aggressive cathode, and looked at the reactivity of EC, FeC, which is fluorinated, is fluoroethylene carbonate 1 proton, hydrogen was replaced with a fluorine, fluorinated EMC, and highly fluorinated ether, which has majority of fluorines here with the exception of 3 protons. So all of the solvents put next to the cobalt phosphate surface, EC had a 1 transfer of proton. If it was allowed to move, it would have another transfer of proton. It would That's very energetically favorable. In a real liquid electrolyte, probably it will not be able to move easily and get another proton because of packing restrictions. It might open up and evolve CO2, as I showed you on that case. But in this case, if it forms VC, it's also very easily oxidizable, right? As I've shown with very fast kinetics. Other solvents also had the same deprotonation reaction occurring. HFE was the only one which had a slightly positive energy, but with enough of the rearrangement fluctuation and might be including anions that could be close to zero and would also deprotonate. And that's, in principle, very troubling story, because at the surface of the cathode, if there are oxygens without protons, then they will all accept at the highest charge state, will abstract H, right? So, and that will be the initial decomposition mechanism. So why this type of system is good? And that goes to idea of Chanson-1 group, because once we created the species and we introduced a highly fluorinated ether, which would also have an abstracted proton, it would participate in the condensation reactions, right? So which are very favorable for the species. And then what you create on the surface, instead of just having EC, which you deprotonate, you after that open it up, evolve CO2. CO2 goes on the other side to the SEI, forms carbonates, impedance there grows. You do not effectively passivate all the cathode, and when you passivate with this type of hydrogenation of the cathode, if fluorine goes to the transition metal, having a OH group makes it easier for cathodes to decompose, right? So you're decomposing cathodes, you're decomposing electrolytes, that's not good. But now we introduce something which has primarily all the fluorines, and that builds a heavily fluorinated interface, CEI, cathode electrolyte interface, which does no longer have the reactivity of protons, and it stabilizes. So that's what it's shown here, that in this electrolyte, in the combination which they optimized, there was a good protective layer which allowed stabilization of this very, very aggressive chemistry. So with this in mind, I want to give more of a summary of trends which we did observe. And this picture which Travis has created, I think is very elegant view of major trends. So we are going to take a fully lithiated nickel oxide, very aggressive, and starts with EC. EC on a fully lithiated surface has a essentially isoenergetic H transfer reaction, right? Once we now remove some lithium, which occurs during charging of the battery, right? Then this energy becomes very largely negative. And the more you charge, the more reactive your surface becomes, right? So in this case, that's the idea for, well, that's when you start limiting charging if you cannot get rid of all the protons, or there might be some other methodologies, right? So that's a clear trend. And another trend is there was a lot of focus on trying to stabilize electrolytes by having high concentrations. That has two sides. One is higher concentration, as I'll show at the end, even for sulfides, it limits their solubility. So it limits solubility of products, which were generated during decomposition, right? So then you form CEI much faster, but also it does have an offset and stabilizes the electrolyte next against H transfer. So when Travis took EC and put lithium FSI next to it, binding to EC, the H transfer became less favorable by about 0.2 eV. Right, so if you go to very high concentration, that might buy you another 0.2 eV, and that's consistent with the say once we have a delithiation of the surface, and energy becomes not 0.6 but 0.38, again close to 0.2 eV. So the stabilization I've seen initial papers suggesting couple EVs due to that. We do observe for this type of reaction, it's only 0.2 EV, but that might be enough to extend a little bit further your charging range and allow more capacity extracted out of the cathode, right? So what happens if we fluorinate? If we fluorinate EC, make FEC, then that's a fluorine here. Then extracting proton becomes less favorable. However, once you removed enough half of the lithium, then that reaction becomes energetically favorable, and you need to go to very high concentration with FEC being actually all of them at the cathode surface being with coordinated to the lithium, then it will be stable. So that's an unpretty picture, which says that in majority of the realistic cases where we want to push reactions, and we unfortunately will have decomposition and have to rely on the decomposition programs for products to be stable. What's about anions? And that is a very interesting case, because I couldn't find decomposition of anions on the surface. We looked oxidatively, but what we found, on the other hand, if we go now to the fully lithiated surface and have an extra lithium on the surface, then there could be defluorination reaction for the FSI anion here, shown here, which is favorable. This reaction, however, is unfavorable for TFSI, which says that this reactivity mechanism is different. And if you want lithium FSI to decompose and form LiF on the surface to protect it further, as part of the more complicated CI, then FSI is a better anion compared to the TFSI. But on the other hand, if cells show you want protection by having as many of the anions as possible on a cathode surface and excluding solvent, then TFSI could be a better choice. What's about PF6? Let's see. PF6 was also found to decompose on a fully lithiated surface and form LiF, and so that's LiF is shown here. There is an important distinction between deprotonation reaction, H transfer. That one becomes more favorable once you have a delithiated cathode. This is reaction occurs when it's fully lithiated. So having somewhere cycling in between helps both of those. That gets me to the last subtopic in this part for oxidation. Can we even get some trends, right? I mean, we can maybe calculate oxidation potential of sulfolane versus EC and say that the EC has a better stability by itself. So would it correlate? And the same as homo-LUMO. Homo-wise, EC would have a higher stability, but does it correlate with the actual performance in batteries? Maybe in some does, but in the case of graphite with lithium nickel manganese oxide spinel, which is high voltage system, what we see is the opposite correlation. Actually, the traditional, not us, but our collaborators, that's Judy and Marshall Schroeder, they observe that it decays pretty fast for traditional CDMC electrolyte capacity, discharge capacity, but in a 3 molar lithium FSI sulfolane, capacity still keeps on. So what it could be, that indicated that could be initially interesting decomposition mechanism, but it's clearly not the oxidation stability correlation. So there should be something else. And in order to understand what that could be something else, we looked more at our methodology for screening at non-active electrodes, because there are carbon particles right all over, and there could be oxidation occurring on them. So we do observe if we have sulfolane, it will obstruct proton to FSI would occur at 4.6 volts. And if all sulfolanes have solvent next to it, it would happen at about 5.2 volts. Surprisingly to me, there was a good correlation with CV of these processes. So when we, again, Judy and Marshall performed CV using lithium FSI sulfolane 1 molar dilute electrolyte, that's the blue line. they observed that there was initial oxidation process at about 4.5, which was similar here, and then a well-developed at 6.5. Once they went to high concentration, when all solvent had lithium next to it, this peak largely disappeared. So it makes us happy, and final oxidation, of course, occurs for both of them at about 5.5 volts. That's on non-active electrodes. What happens on the active electrodes, which can accept protons? Marko Olguin did this calculation. He found that sulfolane next to high voltage Stenel surface has a favorable H transfer energy with a barrier of 0.5, which is indicates quite fast reaction. If now sulfolane is bound to the lithium, then this barrier for transfer stays about the same, but reaction becomes as energetic. So if going to high concentration, we will have a little bit of these reactions, but they will still be occurring, but much less favorable than what happens at low concentration. So concentration will play a role, but why still there is a improvement, right? And still going to be, some of them are going to be decomposing. And to answer that question, we looked what happens after that, right? In a very simple calculation, take a sulfolane with obstructed hydrogen, right? And then try to open it up like I opened EC. There is a reasonable barrier 0.7 volts, and this reaction is actually isoenergetic. So it's going to be very small yield. So very small part will open a ring, and even if it opens, it doesn't want to evolve SO2 the same way how CO2 was evolved. In fact, when can you get SO2 out? Only if this radical sticks around enough to accept, to lose another electron, to have a second oxidation, then it will have a pretty high barrier, 0.9 eV, and yes, then you can lose it. So it's not the most favorable reaction. Instead, it would prefer for sulfolane to react with another sulfolane and have a propagation reaction or condensation reaction. And that will form an SEI. If you obstruct a proton, again, it will favor propagation reaction. So that gets us a second mechanism. Hey, look, if just need to find a solvent which doesn't have upon opening up gas like CO2 evolving, right? If it would prefer propagation reactions, then you can form such a nice CEI film as has been observed on this high voltage nickel metal oxide particle, right? So that gets me to conclusion for the first part, which says that H transfer is very coupled with majority of oxidation for hydrogen containing electrolyte, unless there are double bonds like in VC, right? And the picture should be replaced, as was suggested by this nice article from Switzerland, from EPLF, that really the HOMO and LUMO are often much larger. Sometimes they match like we see. But you're really controlled by the chemical potential, which would include some of this reactivity, and that needs to be taken into account. So there could be, right now, showing you two strategies which have been used to improve stability of electrolytes at the cathode. One is adding fluorinated solvents which still have protons, which can copolymerize and have a high fluorinated interface. So the other one is choosing solvents which wouldn't open up and have gases. So with this, I think it's a good time to take a break, take questions and discussion, suggestions.
Thank you, Oleg. Yeah, I have unmuted the audience, so please feel free to ask questions if you have for the first part. Just go ahead and ask whoever is first.
Yeah, Oleg, hi, I'm Giacomo. Thank you for your first contribution. I have a question about the hydrogen transfer. So you said there is one thing about hydrogen, one thing about proton, but
it's a proton.
yeah, my question is how do you know this? And have you done like charge calculations to see whether there is localization of charge or not?
Right. Yeah. I should have said proton. It's yeah. This radical is neutral. Proton plus AC is charge plus 1, according to quite a few of the charge partitioning schemes.
All right.
Yeah.
All right.
Good point. It's a proton transfer, and the same for the surface.
Okay. So and also for the surface, you did like a molecular charge analysis or something.
Right. Also, I think looking at the spins, and you can again on the surface, what you're generating the same radical, which is neutral.
Yeah.
Right. All right. Unless, that's actually a very good point, depending on the environment, this radical can undergo second reduction.
Exactly. Yeah.
So, but then second electron gets transferred. So first one, it's a proton and neutral radical, and if it sticks around, then the radical becomes a cation. But if radical floats away as neutral, it releases CO2, and then the other part, this part, the open part, that gets oxidized.
Yeah.
And becomes active in attacking other solvents.
I see. Yeah. Okay. Thank you.
Hello. Sorry. Could I be heard?
Yeah.
Hi. I'm Garn Cruz from the University of the Philippines. Thanks for sharing your first half of the presentation. I've been looking into screening screening possible battery electrolytes too, and one of the schemes that I have seen in recent papers is that they use the redox stability, or I think the differentiality in HOMO and LUMO, to screen possible battery electrolytes. Since you presented here that that parameter to screen isn't as effective, do you think that screening schemes such as the ones that I've said a while ago should have a significant change?
I think so. That's what why we wrote in a paper towards high throughput screening, highlighting these two mechanisms, because in a screening you would get that VC is about 2 volts more stable, less stable than AC, and in reality it is about the same stability, but kinetics is 3 orders of magnitude or 2 orders of magnitude higher, right? So kinetics should be incorporated. And that unfortunately, this type of calculations are less susceptible for the high throughput. I had a previous presentations had a graph that showed correlation between HOMO and oxidation stability, and in general there is a line, but there could be 2 volt deviations. So my view, unless you don't care about 2 volt differences, you can use it reliably, but most often 2 volts is really what makes things work or don't work. And the second corollary from here, that majority of the solvents are not stable, right? So HOMO LUMO, what are you looking for? You're looking for stability. I haven't seen a solvent except heavily fluorinated one which would be stable.
Understood. Thank you so much.
Good. So people got recharged. We can.
Oh, Oleg, I'm sorry. I think I didn't start. I didn't unmute myself. I just wanted to ask a very last question related to your first part. So the molecules that you showed, the transformations, they are implied to be in a conventional homogeneous reaction rates, right? So
right. Polarized continuum.
Exactly, but all the actual transformations are supposed to happen in heterogeneous environment. So you have a solid liquid interface, you have double layer, and the solid itself has a significant coupling, electronic coupling to the adsorbate if it's through adsorption. So my question is this: so is it something that's going to change a lot? Because you show the trends that seem to be really nice with the experiments. And number two is certainly that's related, because if you have adsorption, that's more likely to be adiabatic. But I would expect that with such big molecules, one would have quite a big of contribution of non-adiabatic processes. So then the question of adiabaticity should be probably raised. I'm just curious what you're
yeah, and there are also nice studies in terms of what happens under non-equilibrium conditions, right? When if you have very fast rate and many of the cathode particles semiconductors, right? So there might be some, and in addition to the band bending, don't have a good answer. I mean, it's hard to tackle it. What I'm going to show is Janelle's calculation for the double layer, because then they at least tell you about availability of various reactants, right? So if reactant is excluded, it's much harder to react, right? So that's sort of how we are trying to tackle it. And explicit Born-Oppenheim AMD simulations move on the lithium side, which are insightful, but they have a different process, because in the case of reduction, which I'm going to start talking, in Born-Oppenheim simulations, we would have lithium coming out, creating lithium plus and an extra electron for reduction. And it's a different process compared to the open system, right? So we have a closed system in this case, and I know Minoru Tani has done a great job with the constant electrode potential. That's way to go, but it's hard to apply to more challenging system in a straightforward way, right? I mean, great work. Yeah, so we're just taking something like CP2K free code and trying to understand. There are some fundamental challenges on that.
That makes sense. Yeah, maybe then we can continue if the answers might be later too.
Good. And please, other.
Yeah, if anyone has any questions, you can ask, or otherwise we can continue once again. Just.
Good, so let's continue to the other side. On the other side, we are going to use exactly the same thermodynamic cycles, and that got us a reduction potential as in a solvated reduced species minus initial, take a negative sign, divide by Faraday constant, subtract 1.4, and keep again in mind that 1.4 could be 1.6 or 1.2 depending on the solvent, right? But for this purpose, we are going to use 1.4. First question is, what should we screen? If you screen something like VC and calculate reduction potential versus lithium, you get a negative potential, which means that it's going to be stable. Clearly, majority of it's very important to have lithium around, because if you have lithium next to the solvent molecule and you give an electron, right? Electron gets stabilized because lithium polarizes the solvent, gets stabilized in this region, and that without any reactivity, I mean, a sense of decomposition of breaking bonds or anything, that reduction potential already gets increased by 0.5, getting to 0.3. So that gets us to calories. If you want to screen, somebody needs to get muted, I don't know who. If you want to screen, need to put lithium in. The solvent, which is next to the lithium, will have a higher chance of getting reduced, provided the potential is also matched. Also, we need to worry about how well implicit solvent describes the region next to the lithium. Up to some point, because in both reduced and oxidized species here with the lithium doesn't change its charge. So part of the inadequacy of total salvation model, implicit salvation model for lithium, gets subtracted because it's present in both of the species. That's completely not the case. I want to make a point for divalence, because in divalent, if you have a species going from 2 to 1, then your solvation energy next to it really changes. So there, it's one shouldn't apply implicit solvent models without putting a full solvation shell. So want to make one example based upon joint work with Chanson One group, where they came up with a very innovative idea of thinking how to stabilize a silicon cathode. And what they said that instead of having a oxide interfaces of SEI, so carbonates, which bind to silicon pretty strongly, they suggested that having a lithium fluoride, very rich lithium fluoride interface would allow silicon to go and slide and essentially have a framework of lithium fluoride in which silicon would flow in and out as silicon lithiates. And as lithiates, it changes its volume by a factor of 3. So as lithiates inside of the lamellas and SEI, it will have much better performance, and they have shown that that's indeed the case. So the question was, what is the best electrolyte to try to generate almost pure LiF or as much pure as we can? And in order to do that, we can do screening and specifically calculate lithium EC reduction potential, DMC. There is a slight preference for the EC to be about 0.5. Now, the next question I want to address, what if we have a counter dipole from other EC molecules and full salvation shell for the lithium? How much does it change EC reduction potential? And it changes it from that, we're looking at G4 and P2, more accurate method, which was developed by Larry Curtis. It changes from 0.52 to 0.82. So the inadequacy due to omitting completely the first salvation shell is about 0.3 eV. EC in this case get reduced. If we reduce DMC, you can see that it's bent. Then it's 0.65, which is consistent with also DMC reduction being lower, right? Also, DMC contributes less to the first salvation shell, so that comes another relation to the importance of understanding the salvation shell. So EC is going to reduce first, and if we go to larger system of 4, it's similar reduction potential as with 3. Right, so EC will have reduction potentials in the range of 0.8 from calculation. Experimentally, it's close to 0.6. What's about anions? And if we have LiPF6-like anions, and they heavily aggregate, which does happen in pure DMC, but it doesn't happen in pure EC, or in EC DMC 1-to-1 electrolyte. But if some of these fragments would occur, then reduction potential would be about 1.17 volts, and that's another point that DFT here, this relief at least, significantly overestimates this reduction potential because of inadequacy with the lithium, with the fluorine phosphorus bond description. So now we can take LiPF6 with this reduction potentials for solvent, and also look at the and plot them here. So reduction potential for DMC, this one, well, that's the one where DMC gets reduced. That's with AC, that's a light 2, or just with 2 DMC. So my point is that in EC DMC, reduction potentials for solvents are going to be here, while majority of the species are largely dissociated. So there are going to be very few of these aggregates, and more probable species will be something like contact ion pair of lithium PF6. Once we reduce them, there is LiF forming, and that has a reduction potential of about 1 volt, but this relief is known to overestimate. So it gets us to this range of reduction potentials for salt and solvent being the same, right? So if we use this type of electrolyte, we either have to be very, very slow to start initial decomposition due to very small fraction of contact ion pairs, or HF, which is present. That's another process. But solvent is going to contribute, and if solvent contributes, they're going to be carbonates. They will go against the suggestion of Changsen 1 group that we need to form as pure LiF-based SEI as possible. So the next question is, what could be the solvents which would allow the large separation and preferential LiF formation? And PF6 is one of the best salts for that, because it has 6 fluorines to 1 phosphorus, right? So you do form a lot of LiF from 1 anion. So in this case, what we settled on was lithium with THF, methyl THF, which has a low reduction potential, since I'm showing here. So that's a lithium THF and methyl THF. They're close to 0. If we go to more realistic scenario of complete phosphorylation shell, it's about 0.3 volts, right? So THF would decompose, but would decompose only after majority of silicon was lithiated. And before that, this electrolyte is heavily aggregated, so classes like this are present, and reduction of salt would really dominate. TFSI could be similar with THF, except in TFSI, whenever the reduction occurs, as shown here, you need, in order to have this high reduction potential for abstracting a lithium here from a CF3 group, you need to have lithium come into that group and form any contact, which is not very favorable, because lithium starts with being coordinated by oxygen. So it does happen, but it's a very slow reaction. And moreover, you also have lots of oxygens which eventually go to oxides and other components. So for that reason, LiPF6 was chosen, and Changsen 1 group has shown that it performed great in terms of enabling macro-sized silicon with Coulombic efficiency of 99.9%, right? So that's just one of the examples how we can try to use this very simplified calculations in order to choose the target SEI, right? Another way is to try to understand what happens in a more complicated system, right? So in this case, we are gonna go and spend a lot of computational time, and thank you, Travis, for doing these calculations, running CP2K. So we are gonna take 2 lithiums, form a lithium fluoride initial SEI, which is only partially passivating, have electrolyte in between, and that's a periodic system, so another LiF and lithium, right? So the way how we proceed with this, we understand that whatever initial configurations we have in this electrolyte, that's going to influence what reduction processes are going to be occurring. So we want to be accurate, and we developed accurate force field within my AppleNT framework. AppleNT, by the way, stands for atomistic polarizable potentials for liquid electrolytes and polymers. So we use classical simulations to have a LiF accurately representing interface with electrolyte. Run those simulations. In this case, took about snapshots, I think 8 nanoseconds. So they're well spaced in terms of decoherent, right? So the configurations are quite different, but we're also trying to sample realistic environments in this. Then Travis takes them, optimizes to change from MD to the DFT bond lengths, and thermalizes at lower temperature, and then finally at the 333 or 363. And then proceeds with simulations. One of the observations that we see is that whenever you start, you can see not pretty much whatever you want, but there is a correlation between structure and reduction process, which we are going to see. So what we do, we create lots of different replicas. Those are numbered here, replica 1, 2, 3, and so on. And then we looked at the reactions. When they occur, that's the time. It's going to say if it's on positive or negative side, meaning just Z-wise, right? I mean, both of them are anodes. So electrons flood electrolytes through because they're partially passivated, and the all right. So we are going to look what reactions happen. What we did observe that the most prevalent reactions was decomposition of PF6 when it would spontaneously give up 3 fluorines at the same time, not just one, and having local excess of fluorines on this part of the SEI, forming eventually LiF, and none of the solvents would ever decompose. So clearly that supports our previous picture that only PF6 is undergoing direct reduction on a partially passivated surface. The other observations which we had, if PF6 had 2 lithiums next to it, or at least 1 excess lithium, that was more activated. So clearly what we saw before, that having an extra lithium binding and polarizing anions also makes a difference, right? So came up with this picture. Now we have statistically significant reactions, which you can see majority of them PF3 forms. But I want to entertain you with a video, which you can watch all 10 of them on a website for this paper. I'm gonna pick up, hopefully it will work. It does, good. So we are gonna look, that's the time, equilibration time, temperature increases as we're trying to thermalize after changing bond lengths from classical to quantum. Let's look initially at this first PF6. It's going to decompose at 2.2 picoseconds. After that, we're going to look at this PF6. It forms a contact ion pair, and through the other interface periodic boundary conditions, there is also another lithium next to this, right? So now we're getting close. It comes closer. This lithiums, it's important that there is an LiF. They participate in the reaction. Now let's look at the other side. The other PF6 undergoes the same decomposition reaction with PF3 forming, but there is something else. Look at this fluorine, right? Once this fluorine is coming in, it starts kicking out and makes the interstitial fluorine, right? This interstitial fluorine wants to go to another layer, and once it's going there, it's kicking out and putting another fluorine to the other side, and there is a LiF eventually forming on the other side. I think that that's a very interesting insight, because majority of groups had a very hard time understanding why LiF is good, right? Why LiF has a reasonable lithium conduction, while it is expected to have a very, very low conductivity because it has a lithium diffusion, lithium vacancy diffusion mechanism. And of course, if you're next to the lithium metal, you don't have many of those, right? So this type of fluorine, right? So transfer and creating LiF on the other side might be something which is unique to the nanoscale aspect of the LiF-based SEI, right? Because what really matters is not what diffused, but relative diffusion of the lithium to the fluorine, right? So if fluorine moved and readjusted this SEI next to the lithium metal, that's already motion of the lithium to the other side, right? So why it happened? Because locally, when PF6 gives out all 3 fluorines, there is a excess fluorine concentration. So there is a large driving force for fluorine at this very, very thin STI, right? The other thing which we are coming to is at 17.2 on the positive side, there's going to be another reaction, meaning that this PF3 will have another fluorine coming in and joining and then leaving, right? So that's another thing. Just want to summarize this picture. What we saw that those PF6 which were coordinated by 1 and 2 lithiums and also close to the surface, so fluorines would coordinate lithiums to the surface. They then were preferential for undergoing reduction reactions on the surface. And there might be clues for local relaxation, as in a very thin layer, fluorine can also be kicked out due to this 3 fluorines being right next to it, right? So there is a large force to transfer fluorine or lithium out or fluorine in, right? And fluorine transfer seems to be one of the events which we observed. Was it observed only one time? I'm going to show using another trajectory R10 that no, we do observe it. Hopefully it will play. Oh, so no. Previous one played. No, not that. Oh, let's see. Well, then we can save time. You can go watch all 10 movies if you're interested and see that indeed for R10, there is another interstitial fluorine. But I can show it to you also on this picture for another replica. Look, that's the fluorine, which is more in cyan, just so you can see it, which is available. It's gonna come, and as it's coming and wants to replace another fluorine, which is already in a 3rd layer from the lithium of the SEI. Once it's approaching the fluorine, we cover the other 2 which participate in this simultaneous transfer, right? In yellow, right? So once it's coming in, there's another fluorine from the 1st layer gets kicked out. 2nd one also starts moving, and as it enters the 2nd, so it's a very correlated event for the fluorine diffusion, sort of similar to what Yofei Ma was describing a couple years ago in Nature Communication papers, that barrier for the lithium transport simultaneously in many of the solid electrolytes could be lower if all of them move at the same or in a coordinated way. So we think that that could be also the case here. And lithium and fluorine diffusion was primarily looked as a one event, right? Looking at the nanoscale and cooperative events might actually explain why LiF is actually not such a bad conductor, and doesn't matter how it rearranges. If it's on a nanoscale, it can rearrange any way you want. You just need to have relative motion of lithium and fluorine. Wanna go and say that can extend this same philosophy of if you don't want solvent participate in STI and you want to rely on the anion, that is especially true if your solvent is water, because in water you form gas which is totally not good in STI former, right? And also you have OH, of course, forming in. But in the case of water, you need to rely on anion, or at least that's one of the mechanisms. And that's what we have looked at. Specifically, we can take a simple system. It's slightly larger systems than what I originally included in a paper on water and salt. So this system has 2 lithiums bound to the TFSI anion, which is representative for 66% of the anions at 21 molar lithium TFSI in water. And we can look at the reduction reaction when a SN bond breaks or fluorine gets transferred and gets solvated between lithiums. So all these complexes are in a polarized continuum using SMD, either water or 20 lowered electric constant, as it might be the case for high concentration next to the interfaces when the electric constant is lower due to limited ability to relax, right? What do we find at 2.14? Pretty high potential. The TFSI can get defluorinated. Of course, this reaction is going to be very slow reaction because you need to have rearrangements and you have to have lithiums coming in. But crowding, which occurs at the interfaces and which occurs in highly concentrated electrolytes, helps to kick it out and have access to it. The second reaction most probably is going to be at 1.7 volts, ascend bond breaking, and that will lead to the decomposition of the salt. And the Bohr group was proposing another idea with anion being attacked by OH. Travis has looked at the other anion of triflate and found that indeed that could be the case, but with a pretty high barrier of 1 EV at best, and most other barriers are close to 2 EVs. Now, so we can decompose and form fluorines, which will deposit, and solubility is much lower for fluorine in a highly concentrated electrolyte. That can extend the stability window, which has been shown by us and Johnson group as pioneers in water and salt electrolyte. So traditional aqueous electrolyte stability can be extended in a 21 mole of water in salt. That's what Y stands for, electrolyte. And furthermore, they have numerous routes to extend it. One of them was with adding ionic liquid. So then you can put even more salt in, and that extends stability window even further from about 1.7 to 5 volts due to now other species than water competing and undergoing reduction reactions, forming an SEI at high potentials. So now, once I introduce this 21 and water in salt, we want to show MD simulations for the water in bisalt. And specifically, I'm going to take 21 molar. That's the solubility limit for lithium TFSI. However, what Johnson group has shown that 7 molar of lithium triflate, shown here, can be added to TFSI with water, and that has even slightly improved, further improved stability. So the question is, what happens at the double layer in the system? In order to do that, Janelle used constant potential methodology, which he coded in custom code, which allows electrode to be polarized and respond to the electric field and species coming in from electrolyte. And electrolyte, by the way, is treated by my polarizable force field, which has a reasonably good description of majority of the properties in bulk. So we're going to take that, put potentials between electrodes, and see what happens next to the electrodes. Right? So we're going to start with potential of 0 charge and look at the side view and top view of the inner Helmholtz layer next to the electrode. What we do observe, that TFSI and triflate, they have a relative enrichment, which is good, right? I mean, water gets pushed away. There is much less water here. We do observe that they have proximity to lots of lithiums all over in both places. So the lithium is available to remove fluorines from triflate, remove fluorines from TFSI, and also decompose TFSI, and have a anion-based SEI forming as opposed to hydrogen evolution. So majority of lithium with water, they want to go to here. That would be outer Helmholtz layer close to diffuse double layer. There is very good news happening at the positive electrode. So once we put a positive potential, anions come in, water gets completely pushed out. There is no water in the inner Helmholtz layer. There is also another interesting point occurring here, that TFSI comes in, triflate actually gets lower. And that happens because TFSI has 2 oxygens which can be oriented towards the graphite, and the other 2, it's a high concentration electrolyte. So they have to coordinate lithium, right? It's a very high lithium concentration, very little water. You have to rely to anions to both screen the charge and coordinate lithium. However, in triflate, if you have lithium next to oxygens, and that's actually the case, which I'm not going to be showing. then triflate doesn't screen the electrode charge as well, right? So you have to choose either coordinate or don't screen the charge well. That's why if there is no charge, triflate is present equally or proportionally, I should say. While when there is charge, then CF3 group doesn't screen the charge. It still wants to be coordinated to the lithium, so it gets pushed out also. So that, to me, very interesting, because that indicates that there are mechanisms of selective electrosorption, which can be utilized, might be even beyond lithium batteries field, for bringing and changing preferentially surface properties as a function of potential. And clearly, when water gets pushed out, then there is a lack of water coming in. Lithium still needs to get dissolvated from water, get solvated by TFSI in order to intercalate. But that minimizes excess of water, and especially water, which very small fraction, which is free water to the for the oxidation. And free water oxidation-wise would be expected to be preferential, right? So that's where free water is nice. However, on the negative electrode, there was a bad news. Once we polarize to -2 volts, what happens that lithium, as one of the species, wants to go in, and lithium preferentially is coordinated by water. And now it's negatively charged electrode. It doesn't like negatively charged species, which are anions, which is the majority of electrolyte. So anions go to the second solvation. Lithium with water comes in, and unfortunately it brings water. So eventually, if SEI is not very robust and there are cracks developing, lithium will start bringing water, and that's challenge. Highlights challenges at very, very large negative potential for the water and salt by salt electrode. Let me get a summary for this. So if I look at cumulative density only in this inner Helmholtz layer, in water fraction stays approximately the same, then at about 1.4 volts versus potential of zero charge. And if potential of zero charge, you can say that it's approximately close to like 3 volts or something, then that would be 1.5 volts versus lithium. Then below those, titanates and others will get challenging because lithium is going to be coming in. TFSI is increasing as we go to high potentials. Positive potentials, triflate goes back. And I was very pleased when Xiaomin Ren and at IRL put together surface enhanced IR, and he did observe that indeed now we are going from this high potential to low potential. TFSI signal goes down, triflate signal goes up. So at this limited range, he did observe that indeed the selective electrosorption has been happening. Now, I want to summarize this picture of how AA is influencing at pretty high potential, so not very negatively polarized. There is an excess of anions, which is beneficial for the decomposition preferential. What is pushed out, what is especially pushed out at the cathode, says that indicating that there could be an additional mechanism for stabilization of oxidative stability of water and salt electrolytes. However, on the negative electrode, especially if potentials are very negative, you see this potentials, right? If you look what previous seminar speaker Axel, right, when talked about water at platinum as interfaces, that is really ripe for abstracting proton, transferring to the surface, and having a hydrogen evolution reaction. So that's a problem. Therefore, we need to form an SEI for these systems. Or how can we improve on SEI? One of the ways how Chanson Wang group again came with a new mechanism. They said that, well, we can increase salt concentration further, decrease amount of water overall, and increase solubility. So after they put a trimethylammonium nitrate TFSI 21 molar salt, they could increase solubility of lithium TFSI to 42 molar. What it does, it changes the lithium solvation shell from now having a little bit more water than TFSI, right? That's a 21 molar. That's coordination of lithium. That's water. That's TFSI. Once going to 60 molar, now we have 3 TFSIs and about 1 water per TFSI. So we did decrease overall amount of water, they did, but there was another positive benefit. Another positive benefit, now we simulate this double layer structure, then now we see much less lithium bringing in water for 2 reasons. First, there is less water, and second, there is a competition between ammonium nitrate, right, cations, because they're also positively charged. And this ammonium nitrate cations can preferentially scavenge when lithium comes with water, forms the hydroxide. Travis has shown recently that Hofmann elimination type reactions are favorable, so we can have additional contribution to the SEI from decomposition of ammonium nitrates, in addition to what he has shown that there could be slow reactivity through SN2 pathway when OH comes to the triflate anion and decomposes, forming HCF3, which can further lead to the highly fluorinated species. So that leads us to a little bit more understanding of how double layer can play a role, a multifaceted role in terms of stabilization of SEI at different reduction potentials. It also plays a role not only in water and bisalt electrolyte, which are heavily concentrated, and because of that lack of solvent, free solvent, there is this expulsion of solvent at high potentials. However, if we take a traditional ECDMC LiPF6 electrolyte, put it in between 2 electrodes, and start asking a question, what is the structure of the double layer? We do observe that at potential of 0 charge, both solvents are present at proportional amounts of EC and DMC. There are some PF6 coming in, lithium typically is not very close to the surface. Once we get to the minus 3.5 volts, we do observe that lithiums are getting actually partially dissolved. And that brings me to an important question. I did publish, so others, potential of min-force for the dissolution. However, I did it for neutral surface. And as we polarize it negatively, that potential dissolution goes down. Free energy for the dissolution, and it's actually much easier for the lithium to get dissolved, and it's no wonder, right? I mean, we are applying a very negative potentials, so it's easier for lithium to reorient and get partially dissolved. Look at the ECs here; they really standing up like soldiers, right? I mean, very nice alignment. Been in the army, it's all just. Why? I mean, because that's how they rearrange their dipole in order to screen the majority of the surface interaction here. DMC cannot do that effectively. And because of that, EC will have a preferential interaction, as I'll show. Now coming back to the positive electrode, we see both solvents and anions. And the point is that at reasonable concentrations like 1 molar, there is just not enough anions to completely get to the surface of the cathode and expel all solvent. So all species are going to be present. Now let's look at the same, but in a quantitative way. First, we are looking at the lithium coordination number. Lithium coordination number, that's a very DMC-rich electrolyte. So DMC has a slight preference, despite that, slightly high, present in higher numbers, despite EC has a higher preference to coordinate lithium. What happens as we go and polarize it negatively, we see that EC pretty much stays. Lithium starts losing PF6, right? I mean, it doesn't want to have as much of PF6, and that's different from what we observe in bulk simulations, right? So we take structure, bulk structure, say, well, that's that aggregated. Once we polarize it very negatively, it's going to be less aggregated. So that needs to be taken into account when we are using bulk structure to say that's the aggregation number. It will be less on the negative electrode and majority of electrolyte. And the other important ramification of dissolution that DMC gets dissoluted first, right? So lithium comes in, EC stays, DMC gets desolvated first. So there is a preference for the EC to be still, even in a DMC-rich electrolyte, adds to be next to the lithium. And I showed you a couple slides before that it also has a slightly higher potential than Cs come from our DMC. Trans actually, there is a slightly higher reduction potential for trans. So taking into account preference for EMC to be in a lithium for solvation showing slightly higher reduction potential, that leads to the conclusion that there's going to be more EC reduction, and EC is going to be a larger component of SEI as was often reported. Now, what's about just overall species? Because lithium coordination is more important here, but presence of just overall free EC DMC next to PF6 is more important for the cathode, right? So now we are looking at just cumulative density of solvents inside of the inner Helmholtz layer. So in this case, we do observe that as potential gets increased, so from potential of zero charge, DMC gets out of the first layer. It's pushed out by EC because EC can have these carbonyl groups, right? Can rearrange dipole and push out a not very polar solvent, and of course anions comes in and also primarily push out DMC. That was very interesting and tells you that the actual structure at the cathode interface is quite different. That was reported a while ago. I still like this result, especially because next year Japanese group reported some frequency generation, where they said that while in bulk in this CDMC electrolyte there is a slight preference for EC. We observe they observed in good agreement with our results that the interface is really preferred by EC compared to DMC, which is very consistent with this type of charge interface. Of course, there are other effects due to oxides and specific absorption, but that gets at least a positive electrode charge contribution, how it influences selectivity of species to be absorbed at the interface and participate in reactions. Now we are done with this next part, and it's a good time to ask questions.
Thank you, Oleg. Maybe I can start by just, if you go back one slide back to your the interface that you.
Okay. Or just this?
For example, yeah. So my understanding is these calculations, they don't take into account any quantum mechanical coupling with the electrode, right? So it's just pure electrostatics.
Yes, I mean,
in terms of the solid liquid
simulation, no reactivity here. That's absolutely right.
But in that case, so if you do try to include reactivity, at least for one of the configurations, would you, so say you do DFT, MD, a pretty heavy calculation, would you expect a significantly different picture still? Or it would be pretty much the same and you don't expect that absorption, specific absorption or chemisorption, especially electrochemical chemisorption, would affect the double layer structure significantly?
I would expect that, and that's why you're right. That's why in previous work on von Oppenheimer, we did include specific LiF because unlike pure simulations on lithium where electrolyte gets flooded with electrons and everything gets reduced, or nearly everything gets reduced, now we have some specific surface, specifically lots of lithiums, right, to take fluorines from PF6, and fluorines get absorbed essentially, right, on a lithium and LiF, creating excess of fluorines, but they do get absorbed. So it's important to have specificity. It's true. In order to do that, just never published, we had similar work of I put barrier charges underneath of LiF, right? So now you combine and ask. So there are, of course, similar effects, but there are peculiarities there. So it's a very good question. Just you need to finish that, get it out. How LiF passivated cathode would actually, I mean, what's the difference on that double layer versus the double layer on just graphite? I can tell you one thing, we did look at the lithium-ion phosphate previously. And of course, what you see there is that carbonyl group binds to the transition metal, and then for EC and in EC, the other, it's in opposite direction with the ethylene group going towards the oxygens, right? So you have this, yeah, exactly this type of opposite dipoles, one at another. And there are similarities to what happens here, right? But there are specificities. There are specific points, specific routing, and that's where different surfaces, as has been shown by many, by Argon group, right? Kim and Kevin has shown that also for the cathode, take different surface, you will have slightly different reactivity because oxygen's alignment is different, population of lithium is different, exposure to transition metal is different. So there is a question, what do? We typically start with the most available one, the lowest surface energy, right? But
not like oxides.
Yeah.
Okay, and the other thing is, I noticed that you once mentioned that DFT is not quite adequately describing the PF bond in liquids, right?
Right, that was this relief. That's correct, and so we switched to Martin potential WB97XD for that reaction, and MO52X works better there. So that's MO6L. I did look at that, predicts a much lower potentials for many things. So there are many tricks, and there are like this, you need to pick the one which is more adequate, right? And the one which you can also run. What is very interesting on this subject, that lithium binding is much better described by TBE fast, right, than bis relief. Bis relief overestimates binding energy of lithium to EC by about, I think, 4 or 5 kilocalories, which is very large. So if you parameterize force field, don't use that for parameterization. But for relative energies, it does okay.
Okay, that's very good. Okay, we have one question from the audience.
Oleg, thanks again. Really fantastic work. So I have a question regarding sort of the general computational procedure that you use. I mean, these are highly heterogeneous systems with a lot of flexibility and different chemical species in it. So I'm sort of wondering how much sampling do you need, and how much you need to equilibrate your systems, for how long do you have to like go through, even in the case of using DFT, do you have to go through force fields before, or Monte Carlo? I have this sort of general question.
Right. I love the question because it hurts to see when so many works does the following: uses MD without saying how accurate that force field for the particular one was, right? Generates initial configurations, then does 5-10 picoseconds, especially in a high concentration realm.
Yeah.
DFT simulations, right? And I know that in 5-10 picoseconds, lithium doesn't exchange solvent. It just vibrates a little bit. And then when I have no problem overall with the picture, but it's not the DFT structure, right?
Yes.
So that's a very, very important point. So when we did Bonn-Oppenheim AMD to understand, for example, zinc structures, right, with zinc triflate, for example, if we put it even at high temperature, aggregated or TFSI, it over 30-50 picosecond doesn't dissociate. So all that we can do there is just rank different geometries. What I typically look as the residence time, of the lithium next to solvent next to anion. So the run should be longer than the residence time. So this way to sample at residence times, for example, in ECDMC are about 100 picoseconds at room temperature for ECDMC, so that you can equilibrate, and about 200 picoseconds for the PF6 at higher concentration. There, if you raise temperature, you are doing fine, you can equilibrate. So what we do in Born-Oppenheimer, when we really want to get structures, set it up from two completely different aggregation states, ensures that it goes in.
Yeah.
Cost a lot of time, but I cannot agree more with the fact that 5 picoseconds simulation runs reported not reflective.
All right, thank you again.
Thanks. Axel, I noticed that you were the last.
It's very nice to see you. This is Axel.
Nice to see you.
Yeah, I mean, I can't switch on my video, I think. But okay, first of all, I had a remark which I put into the chat with respect to the stability of electrolytes. And I don't know whether you came across the paper of Pelio and Giraud from 2018, which impresses, let's say, that is a misconception that the homo-LUMO gap really determines the stability, and it's rather the electrode, the oxidation potentials, and the simplest example which you all should be aware of is water. Water has a homo-LUMO gap of 9 eV, and it has a stability window of 1.23 volts. So in principle, I always tell my students, don't believe everything that Nobel laureate says. It can be really nonsense, so to say. But this. Let me ask one question. I'm a little bit overwhelmed by all these details. So you talk a lot of the decomposition products that could be the initial products for SEI formation. Now I want to challenge you a little bit. Can you really then determine the structure of the SEI? I mean, or is it only the first steps? And what to do? I mean, this is, I think, the ultimate goal. Or we would love to know a little bit more about the structure of SEI, of the SEI.
Right. So maybe it's outspoken philosophical comments on this. It's only initial stages, but if solvent and PF6 are well separated, right? It's the majority component, so it's easier to predict. When there is a soup of things, it's very tough. And one of tough things for me, for example, when I took lithium ethylene dicarbonate, right? When it forms, put it in solution. I do see initial aggregation, but even if I run hundreds of nanoseconds, the final solvent never goes out. Okay. So what I think happens, well, first of all, that's a time scale issue, and just a very, even in a formed SEI, just how to get the solvent out and compacted. SEI becomes porous, right? And if SEI becomes porous, like Arnaud had a nice paper on what diffusion inside of the pore of the species convection, can bring and reform it. That's very tough. There are lots of, well, not lots of, there are more and more work now when there is the kinetic Monte Carlo is used. Very pretty pictures, something which matches cartoons. However, what is challenging there, that how to take into account this extra reduction in a porous species, mass transfer limitations. SEI, in my view, forms seconds, minutes, right? And this mass transport limitation, if you do coarse graining, where it's much faster, then relative rates are also different. So
okay, it's a challenge.
It is a challenge, and that's why with limited resources we stick with the initial stages.
Okay, thanks for this.
We have 2 more questions. I'm not sure. Should we leave them for the end, or?
Let's ask now. I would rather have this finished other than last part. Yaros, Samara.
Hello. Thank you for your presentation. I am Jairus Samera from the University of the Philippines. For slide 21, I would just like to clarify what determined the choices for your electrolytes.
So that was a hypothesis by Chanson and his group that if LiF is the major component, then because it has the lowest binding energy with the silicon and lithiated silicon, silicon can slide back and forth, and this way it doesn't bind to the SEI and doesn't cause the SEI to expand together with silicon, right? So that was the hypothesis. Because of that, let's have the richest SEI component with the smallest impurities possible, and that's why we were trying to get the largest separation, and also anion, which gets the smallest byproducts, right? Like PF6 gets you 3 LiFs and PF3 gas, right? Doesn't give you oxide, sulfates, and all other things. So that was the motivation.
Thank you.
And Jan?
Hi, hi again. I'd like to ask a question about your simulation, I think on slide 25, I think. So you're using, I think, LiF here as your SEI, but I think that, if I recall, I think SEI, it follows like a mosaic model that is composed of different decomposition products from electrolytes.
Right.
I was wondering, could this methodology be applied for such an SEI, like a mosaic of different components, or is that something that is still in our time very highly unrealistic?
My personal opinion, I mean, let's look at the challenges. So typically I show another slide which shows not 3 layers, but I think 9 layers or 8 layers. So in 8 layers, you have a larger computational system, right? And it's now you start becoming get more reasonable rates. But you would be lucky if in 20 picoseconds you see one event, right? So that's sort of partially answer to getting more realistic SEI. What is true is that here the rates are much faster. The reactions are on a picosecond timescale instead of what you would expect, orders of magnitude faster, because of this very small passivation layer. But at least it has a chemistry of the SEI, right? And we use lots of sampling. So we're thinking initially like maybe that's yes, we're at low potentials, but with lots of samples, we get qualitatively the same picture. What should be included is grain boundaries and between different SEI components, but it's harder to do because here we need to choose lithium dimension in such a way that it would conform to the LiF on the length scale without having much of the strain on either of them, because then lithium starts buckling. And Travis has gotten good lengths to find this good match, right? So now think if you have 2 components, it becomes even harder unless you have an amorphous soup. If you have an amorphous soup, that's a good question what happens. So that, I guess, the best short answer I can give.
Thank you so much. That was very helpful. Thank you.
Good. So let's have a final part, which is going to be very short. Just want to highlight some of the interesting things in lithium sulfur batteries. Because lithium sulfur batteries take a lithium sulfur. One of the big problems is that there are longer polysulfides forming, and longer polysulfides, if we take a classical DME, dioxylane lithium TFSI system, this higher plateau is typically formed by longer polysulfides, while lower plateau is described like 2 to LiS conversion. So now the question is that what this plateau, due to solvated species, which have been a lot of work done and identified, can we get rid of it? Because if we remove the solvated species, reduce their solubilities, and they're going to be less shuttle in the lithium sulfur cells. And turns out if we take a diluent approach of what PNNL calls highly concentrated localized electrolytes, meaning that there is a solvating species of sulfolane with a lithium TFSI salt, and we put diluent, and following their work is just TTE, or highly fluorinated ether diluent, then lithium salt will segregate to the sulfolane domains, right? Now locally it's going to be very, very high concentration regime. And how does it change? So Lab Fusion group has looked at two concentrations, 1 to 2. 1 stands for sulfolane, 2 for diluent, and put in much more diluent, as 5 times more than sulfolane in this system, and trying to keep also low concentration, relatively low concentration of lithium TFSI. And what happens that in this system with just twice as much diluents, and there are still 2 plateaus that's showing different rates. And once there is a very large amount of diluent introduced in a system, there is only 1 plateau. Second plateau is shrunk to a very small number. And that does help with capacity retention, coulombic efficiencies, and prevention of shuttle. So I performed MD simulations of these 2 systems, highly fluorinated ether to sulfolane, that's little diluent, and a lot of highly fluorinated ether with sulfolane. So what I'm showing in blue here is sulfone and lithium TFSI domain, and I also put a Li2S4, this type of longer polysulfides, which are typically known to be in a shuttle. What we do observe that there is some aggregation of sulfates in both electrolyte. However, there is a major difference between that. First of all, clearly, once we put a lot of diluent, which is here shown in wireframe, that nanodomains very localized, of course, of sulfolane with TFSI with a Li2S4 form. And when they form, what happens that a Li2S4 essentially gets pushed to another Li2S4, and it's no longer fully solvated. And how do I know that? If I look at the radial distribution function, and I'm looking at the overall sulfur, those sulfurs in 5:1 HFE to lithium, we see a very large peak at short distances. At the other system, while there is again, so that's this black line, while there is a aggregation tendency for them, they do phase separate eventually and aggregate, but they are separated by solvent. So it's a solvated species versus non-solvated species. And I wanted to put forward as a suggestion I think it's in agreement with what Yuchi published with Chanson Wan recently in Nano Energy, that solvated Li2S4 has contributed to this potential 2.4, but desolvated has a lower potential and gets converted to Li2S much faster. So that's another interplay between pushing solvents together by putting a diluent, and that is beneficial for Li2S. And somewhat similar picture was observed previously in Chonin work from Chanson Wan group, where he used a bisalt water electrolyte, and there he observed 1 plateau. And also in this case, Li2S2 really essentially, it's a very slow system, so I haven't completely equilibrated, but what I'm showing here is that they essentially got stuck one on top of each other and started phase separating. Li2S4 was much less so, but it was partially desolvated. So there seems to be a correlation between desolvation and pushing of Li2S4s together versus just segregation in one area, which affects potential. Now, on the last slide, 2 slides, I want to get to the completely different issue, and that gets to excellent work by Georgia Tech Lab Fusion Group and Fei-Shan Wu, who observed, looked at the mixtures of Li2S with sulfur, so it generates sulfides and different electrolytes. So initially, they looked at 0.1 mole of lithium TFSI, 1 mole, and 3 mole of lithium TFSI. What they did observe that 0.1 molar had the lowest solubility, and also despite the lowest viscosity, fastest electrolyte. Solubility was low, and also the dissolution process was low. 1 molar was the fastest, and 3 molar was the intermediate one. So I did in a joint collaboration, with them, performed MD simulations, took again Li2S2, Li2S4, and combined mixtures of put it in MD simulation both, so Newton equation of motion, got the trajectories, and wanted to validate the force field to see how accurate it is, because ultimately we don't want to give a wrong provide wrong conclusions. So one of the ways I found very nice data from PNNL in a joint paper of PNNL with Christine Person Group from Berkeley, where they reported diffusion coefficient for both DME, dioxylane, TFSI, and lithium. And what I'm showing here is 1 molar lithium TFSI. MD are open symbols, and MR field symbols. I was very pleased with this agreement. Even if we went to high concentration lithium TFSI, both species diffused accurately, and they had also data for lithium in a mixture of Li2S4. And why I think that that's important in DME dioxylane, so there is an excellent agreement here. What I also did, I said, okay, now I'm gonna just make Li2S4 aggregate much more. And when I aggregate that much more, it changes lithium diffusion, it drops dramatically. So that to me is an indirect evidence that with non-reactive force fields, there is non-interchangeable species. Just want to be clear here. So that's a downside, but we are taking this Li2S4. I think it's a reasonable description of how aggregated species are and how solvated they are. So what I'm going to do, I'm going to take 3 salt concentrations of 0.1 mole of lithium TFSI, 1 mole of lithium TFSI, and 3 mole of lithium TFSI using the same DME dioxylane mixed solvent, and look how concentration of that main salt affects aggregation of this other salt, like Li2S, Li2S4, in this case, Li2S. And what found was somewhat surprising, right? At 1 molar, there was the least aggregated. There were local aggregates, but it wasn't the phase separated. Once I decreased salt concentration, essentially all Li2S4 went to one cluster. Very highly aggregated system. In high concentrations, there was also increased clustering. So typically in this area, there's a lot of work from Watanabe, high concentration was attributed to reduced solubility and high aggregation, because what happens now, you take put more salt, and each lithium takes a solvate, gets solvent to be solvated. So you are exhausting, or you have a very small number of available free solvent to solvate the other salt which you're introducing, right? So that's typically the explanation provided for the high concentration. And clearly at low concentration, you do have plenty of solvent, but it's even much more aggregated. And quantitatively, we can look at it here as this RDF for sulfur from Li2S2. 1 molar provides the lowest aggregation. 3 molar aggregation of sulfur increases, and 0.1 molar is the largest. So what it seems like also the anion mediation and screening, right, via ionic strength-like effects also affects solubility of the other salts. And I think that that has ramifications beyond LiS too, because we are talking about solvent, which is just reasonable. So, I mean, no, not great, not super weak, super strong, and strongly dissociating salt like TFSI first, right? And the other salt is very reminiscent of what you get for SEI components, which is very strongly aggregating salt. So there might be some interesting relations of trying to adjust and have a better performance of a battery with low concentration, provided there is still enough transport, by adjusting solubility of the other components and forming a different SEI or forming SEI more efficiently. So that is in a very good agreement, I think, with the picture which Gleb's group provided. And the other point I want to make that when I simulated mixed salt Li2S2, Li2S4, these aggregates of Li2S2, they often were joined by Li2S4. So even if by itself Li2S4 is more dissociated, when in a mixed system, it tends to join the other aggregates, and then it will participate in these reactions. I think we are about out of time. So I want to conclude to say that batteries are pretty challenging with multiple effects starting from double layer structure and availability to come in to homoluma being essentially non-relevant for the battery electrolyte optimization, proton transfer happening routinely on the cathode surfaces, and even on glassy carbon or on carbon additives at high voltages. And lithium interaction is very important for understanding and controlling preferential reduction. So thank you for your attention, and I look forward for suggestions, questions.
Thank you, Oleg. We're open to questions now. Maybe I can start by just getting a little bit back to the general concept. So when you speak about the what I would call a multi-solvent electrolyte, so there are many solvent species, maybe the same salt, but many solvent species. How would you evaluate, or maybe you can comment on the role of the solvent entropy, configurational entropy of the solvent in the stabilization or destabilization of the reactants during these reactions? Because one can imagine that the configurational entropy will depend on the number of components, right? On the way that they can coordinate to the molecule. The molecules are big, so you have lots of possibilities. So I'm curious, is it something that people really look at in this field?
I've seen nice study, for example, from Artem Baskin saying how temperature affects relative stability of solvents, right? So that goes to the direction which you're pointing to, right? Because that gets entropic effect, temperature, entropic, TS effect on different stability of different complexes. What I can say is that typically the higher the temperature, the higher the aggregation rate. That in polymers often leads to salting out very high temperatures for polymer electrolytes. That's probably the closest. So, and one of the challenges in battery area is that there are so many fundamental questions, but also a great need for the empirical progress with the simple systems. So I'm trying to balance it in our group, which is the army very small.
Yeah, absolutely. I mean, that's why I'm asking these questions, because I think it's important also to have an insight into the other part of the studies of the experiments that people do. So I see one person who's interested in asking questions.
So?
Hi, very great talk. I'm actually a big fan of you. I read a lot of your papers. Yeah. So I have a quick question. As you show here, so when you develop the force field for the lithium-2s2 or lithium-S4, do you have any covalent interactions between the lithium sulfur, or just cation anions? Yeah.
I don't. And you see, there is an interesting point. It's a polarizable force field. So originally, if you look at the partitioning of charges in Li2s2, Li2s4, do charge analysis, RESPER or something like that, you will see a lithium charge should be like 0.7, 0.6, very low, right? But then if I take the same grid and look at the effect lithium when it polarizes sulfur, it just induces so much of electric field towards it that I can describe accurately Li2s2, Li2s4, Li2s binding energies with just polarizable force field and Buckingham potential. So I don't need covalency to describe them systematically. And that also gets me accurate structures of Li2S. I was surprised that how well the force field does from that perspective without any covalent. So I think the reason people talk a lot about, so you need covalency when you break sulfur-sulfur bond. So for that, Andre van Duyn had a reactive force field that, so I'm not doing that, right? I'm just describing lithium-sulfur interaction if sulfur bond doesn't break. So that can be done with polarizable force field pretty accurately, I think.
Okay, thank you. Thank you. I totally agree with you, because if you look at the diffusion simulations, it's quite, very agree with this experiment. So, okay, thank you so much.
Say it again. I mean, what is bad in diffusion?
Oh no, I'm not saying bad. I'm saying the diffusion simulation is impressive. It agree with the experiment. So it means that in this case, the polarizable, already take care for the
Right. All right. I got it. I didn't understand it. Yeah, it does better without any scaling of charges.
Okay. Thank you so much.
In terms of scaling of charges, I want to make one point here. If I use a model for water, when I do, which has a slightly lower polarizability of 0.14 instead of 0.44, there I do scale charges by 3 to 6%, 2 to 6% sometimes, because it's not completely polarizable. But if polarizability is fully included, then I don't scale charges.
Okay, great, thank you.
No more questions. So maybe I can then ask the last one, and we will wrap it up. 1 second. Yeah. Oleg, so one thing that I just a second. Okay, I can hear. I can see it because I didn't see you here. So one thing that I'm wondering is just going back to the basics of your calculations. So you look at the molecule, you calculate the vertical ionization energy of the molecule, right? And then you relax it and you look at the final configuration. That's how you can get the activation energy for that molecule. But that's
Very general make a loose connection with kinetics.
Yeah, sure. But my question is not into the kinetics itself now, but more into the actual calculation scope. So when you work with such big molecules, I can imagine that probably in some cases, the molecules become bigger than the double layer. So in some way, the assumption that you should excite from the home orbital of the entire molecule is not quite applicable to the electrochemical process, or not quite connected, because maybe you need to actually look at the excitation from a different orbital within the molecule that is closer, or maybe within the double layer, where actually the electrochemical reaction should be happening.
So
would it mean that you actually have to look not sort of at the home of the entire molecule, but more at the orbitals that are pointing toward the double layer?
Yeah, had a very nice collaboration with Hans and my Tony group on trying to understand more in terms of potential for decomposition of PF6. And it's not quite an answer to what you have, but what I was saying that, look, cheapest way is to include a nanocluster, which would form, right? And say how this nanocluster is shifting and making, for example, the same LiF formation. So this was a nanocluster of LiF, and if it's present, then we don't need the second aggregated species. As you've seen also in the Born-Oberheim AMD, that it does work by shifting, right? So I don't know if you noticed, but that PF6 before reduction, it sort of moved closer, which allowed activation, right? I mean, allowed polarization. So it's the same here idea of you can try to do the same in a cluster, right? So if nanocluster forms, that nanocluster also shifts your level in this case, LUMO.
I see. And then you calculate the energy for the vertical orientation.
Also reaction overall, right? Because your reaction, a final reduction reaction will depend on what is polarizing it, what the environment is.
Sure.
So that's the cheapest way we can do it within a couple of days instead of months.
Okay, then probably this is it for today. So thank you again, Oleg, for a very exciting and quite exhaustive talk, I would say. I think we will have to look at that again and again a few more times to digest all the information. So it was quite insightful.
We want to thank the audience for great questions, clarifications. It was nice, at least to hear you in this era of pandemic and see many of you. Bye-bye. Thank you again.
Thank you so much.
Oleg. Bye-bye.
Thank you, Andrew, for organizing.
Absolutely.
I almost forgot it. It's a lot of work, but I enjoy. I'm a fan of the series.
Yes, as usual. Thank you.